Hello guys, so I'm Farhana. So today we're going to talk about fundamental theorem of calculus. So let's go. So what is the fundamental theorem of calculus? And how can we use this fundamental theorem of calculus? So I will explain all of this in this video. So what you will get from this video is, first you will understand the definition of first fundamental theorem of calculus and second fundamental theorem of calculus. Second, you will know how to use fundamental theorem of calculus to evaluate derivative integrals and definite integral. Third, you will know about the relationship between differentiation and integral. And lastly, you will be able to think about the application of integral in real life. So let's take a look for the definition of fundamental theorem. In part 1, let's say I have some function which is fx is continuous over an interval ab, and the function capital Fx is defined by, so let me draw first and then you will see it clearly. So I have my vertical axis and I will label it as y and horizontal axis as t so that we can save x for later. And then we have the graph here. Now our lower point is a and upper point is b. So now let's define some new function which is the area under the curve between a and b. So I will put some variable between a and b which is x. So we will find a new function that have area under the curve between a and x. So capital Fx is equal to definite integral from a to x ft dt, where x in interval a b. So in the fundamental theorem of calculus in part 1 tell us that the derivative of capital F of x, which is the same thing that the derivative of this, which is definite integral from a to x ft dt, is equal to fx, which is the original function. From here we know that every continuous of fx has antiderivative which is capital F of x, and they have a connection between integration and derivative. The fundamental theorem of calculus in part 1 often called as a cumulative function because it represents the accumulation of sign area, which is positive or negative, under the curve. Let's take a look for the example here. Using the fundamental theorem of calculus in part 1 to find the derivative of fx if f prime of 3. We got the function here which is fx equal to definite integral from 0 to 3x 5t squared over 2t minus 1 dt. So what we have to do is, according to the fundamental theorem of calculus in part 1, which is fx integral a x ft dt, is if x continuous on a b, then capital F prime of x is equal to fx. So we just derive here and we just substitute the value of t with 3x and substitute the value of x with 3, and then we got f prime of 3 is equal to 405 over 70. So for example 2, let capital Fx equal definite integral from x to 6x to t power of 3 dt. Find the capital F prime of 5. Now what we have to do is, since the limit of integration are variable, so we need to split this into two integrals. So what we got here is the function. This is the function, and then we got x here and 6x here. So we want to find the definite integral between x and 6x. So we need to subtracting it from 0 to 6x minus 0 to x. So we get x to 6x. Since we take from x to 0, so we need to change the position. So we got negative sign here, and then so we can differentiate, and then we got negative 2x power of 3, and we got 2592x power of 3. So we just substitute the value over here and we get 2590x power of 3. Go to the definition of the fundamental theorem of calculus in part 2. So in part 2, f of x is continuous over an interval ab, and capital Fx is the any antiderivative of fx. But the formula a little bit different here because we need to find the integration, or we need to integrate the integrand first, and then we have to substitute the value of this limit, which is f capital Fb minus capital FA. So what the fundamental theorem of calculus in part 2 tell us is, the fundamental theorem of calculus in part 2, also known as evaluation theorem, which is we have to evaluate the integrand, state that can evaluate the definite integral by evaluating the antiderivative at the endpoint of the interval and subtracting it if we can find an antiderivative for the integral. So let me show you how the fundamental theorem of calculus in part 2 relate from the fundamental theorem of calculus in part 1. So in part 1 we got this formula, which is capital Fx is equal to definite integral from a to x ft/dt. But now in part 2 we got the definite integral from a to b fx dx is equal to capital Fb, which is the antiderivative of b minus the antiderivative of a. So how can this relate? So first we have the graph here. We know that the capital Fx is equal to definite integral from c to x ft/dt, and we know that capital F prime of x equal to fx. How can the antiderivative of b minus of the antiderivative of a? Let's say we have a between c and x here, and we have b between x and d here. So to find the area under the curve for b is between c and d, right? And then to find the area under the curve for a is between C and A. The area from C to B minus the area from C to A, we got the area from A to B. So we can say that the definite integral between C to B ft/dt minus definite integral from C to A ft/dt. So we got the definite integral between A to B ft/dt. So this definite integral is equal to antiderivative of B minus antiderivative of A. So let's continue with the example. Let fx be definite integral from 1 to 4 to x over 7 dx. So for step 1, first we have to find the antiderivative for the integrand. First, we put out the constant value, which is 2 over 7, out of the integral, and then we integrate the x. So we got 2 over 7 multiplied by x, the power of x 1 plus 1 over 1 plus 1. And then we got 1 over 7 multiplied by x squared plus c. In step 2, we just substitute or compute the value in the function. We already find the antiderivative for the function, for the integrand. So we just compute the value. And we got 15 over 7. So what is the application of the fundamental theorem of calculus? First, we can find the area under the curve. Okay, we just using the formula from the fundamental theorem of calculus in part. And second, we can find the distance, velocity, and acceleration. But we have to modify the formula first. For example, we have acceleration AV is equal to cos phi t, where the velocity at t equal to 0 is phi. To find the total distance traveled in the first 2 seconds. So first we just use the formula here, and then the limit is from 0 to t. We integrate this function and we got the function for the velocity. Now we have to find the total distance. So we just integrate the formula again. Then we got 4 over 5. We can find the volume and use the formula. So it's time for the exercise. Okay, question 1. Evaluate the following integrals. So we got the function here. So for the solution is constant value out of the definite integral. And then for this question, since the x have constant value, so we need to use chain rule. So we let u equal to pi over 2x. When we differentiate it, we got pi over 2. So we got x power of negative 1 over 2 plus 1 over negative 1 over 2 plus 1 multiplied by sine multiplied by 2 du over pi. This is the value back, and we compute the value for the limit, which is 10 and 3. We got the answer is equal to 8 square root of 3 over pi. Alright, for exercise 2, this is the application in real life. Question is, Lily and Daniel are racing at the park. They race along a long and straight way. Whoever runs the farthest after 6 seconds will win the prize. If Lily can run at a velocity of ft equal to 40 minus 6 feet per second. And then you can write at a velocity of ft equal to 2 plus 7 sine pi over 2t feet per second. Who is going to win the prize? Okay, we need to integrate the both function on interval 0 to 6. So for Lily, we got definite integral from 0 to 6, 40 minus 60. And by using the power rule, we get 2t squared minus 60 for limit from 0 to 6. Complete the value. And then we got 30. Step 2, we calculate for Daniel. We got definite integral from 0 to 6 to plus 7 sine pi per 2t dt. By using chain rule, we get 2t minus 14 pi cos pi over 2t. And then we just compute the value here. Then we got approximate 20.90. So since Lily are farther than Daniel, so we win the prize. So that's it. So thank you so much everyone for watching. Bye.